Hello my friends and welcome back to Sky Creative Channel. Today we're taking you inside some of the world's most advanced manufacturing facilities. From multi-axis precision machining to massive steel processing, you'll see how today's manufacturers achieve incredible precision and efficiency. Let's get started. Here we have the remarkable Integrex i4 OOST, a true marvel of modern manufacturing technology. This multitasking machine represents the pinnacle of precision engineering, capable of performing multiple complex operations in a single setup. What makes this machine extraordinary is its ability to combine turning, milling, and drilling operations with incredible accuracy, reducing production time by up to 60% compared to traditional methods. And watch closely as we witness interpolated turning using the mill spindle. This fascinating process allows the machine to create perfectly round surfaces using a rotating cutting tool rather than the traditional method of rotating the workpiece. The mill spindle rotates at high speed while following a circular toolpath around the stationary workpiece. This technique is particularly valuable when working with large or irregularly shaped parts that would be difficult to rotate in a traditional lathe. The precision here is remarkable. We're talking about tolerances measured in thousandths of an inch. The computer-controlled system ensures consistent surface finish and dimensional accuracy throughout the entire operation. Now we're seeing helical gear cutting in action, followed by the innovative Invo milling process. Helical gears require incredibly precise angular cuts to ensure smooth power transmission. The Integrex uses its B-axis rotation capability to maintain the perfect helix angle while the cutting tool removes material. NTHE Invo milling process you're witnessing creates involute gear tooth profiles with exceptional accuracy. This method generates the precise curved surfaces that allow gears to mesh perfectly, reducing noise and increasing efficiency in the final assembly. The machine automatically adjusts cutting parameters based on material properties and desired finish quality. Here's pinch turning with B-axis contouring, a process that showcases the machine's remarkable flexibility. The workpiece is securely held between both spindles while the B-axis tilts to create complex three-dimensional contours. This technique is essential for manufacturing components like turbine blades or propeller sections. NTHE pinch turning setup provides exceptional stability during machining, allowing for aggressive cutting parameters while maintaining surface quality. The B-axis contouring capability means the machine can create compound angles and complex curves that would require multiple setups on conventional equipment. And watch this impressive variable lead grooving operation using end mill side cutting. The cutting tool follows a helical path with continuously changing pitch, creating grooves that vary in depth and spacing along the workpiece length. This technique is commonly used in manufacturing specialized fasteners and threaded components. And finally, we see simultaneous 5-axis machining on an inclined surface. All 5 axes move simultaneously, allowing the cutting tool to maintain optimal cutting angles while machining complex geometries. This capability eliminates the need for special fixtures and enables the creation of parts that would be impossible to machine using traditional methods. NTHE Integrex i4 OOST represents the future of precision manufacturing, where multiple operations are seamlessly integrated into a single, highly automated process that delivers exceptional quality and efficiency. Welcome to the impressive facilities of Bremen Machinery, a Dutch company that has been at the forefront of heavy plate processing technology for over a century. Today, we're witnessing their capability to handle, roll, and bend massive steel plates up to 100 millimeters thick and 4,000 millimeters wide. That's nearly 4 inches thick and over 13 feet wide. This level of heavy-duty processing requires not just powerful machinery, but also sophisticated engineering and decades of accumulated expertise. The plates we're seeing processed here will become components for ships, bridges, pressure vessels, and other critical infrastructure projects around the world. An NTHE first challenge in working with plates. This massive is simply moving them safely and precisely. Watch as Bremen's overhead crane system, equipped with specialized lifting magnets, carefully positions a steel plate weighing several tons. These electromagnetic lifting systems can be precisely controlled to ensure even weight distribution across the plate surface. NTHE handling system includes automated positioning equipment that can rotate, flip, and precisely locate plates for processing. Safety is paramount here. These plates can weigh as much as a small automobile, so every movement must be carefully calculated and controlled. Notice the precision measurement systems being used to verify plate dimensions and thickness uniformity. Laser measurement devices scan the entire plate surface, creating a digital map that guides the subsequent processing operations. This data ensures that the final product meets exact specifications. even when working with plates that started with slight variations in thickness or flatness. Now we're witnessing the heart of Bremen's operation, the massive plate rolling mill. This 3-roll pyramid configuration uses enormous hydraulic pressure to gradually bend thick steel plates into cylindrical shapes. The bottom rolls support the plate while the top roll applies controlled pressure, creating a consistent radius along the entire length. NTHE rolling process requires multiple passes, with the plate being fed through the roll several times while gradually increasing the curvature. Watch how the operators carefully monitor the process, making fine adjustments to ensure uniform bending. The hydraulic systems can apply hundreds of tons of force, yet the control is precise enough to create perfectly smooth curves. Temperature control is critical during this process. The steel plates are often preheated to reduce the force required and prevent cracking during bending. Infrared sensors monitor temperature distribution across the plate's surface, ensuring optimal conditions throughout the rolling operation. Here we see the press brake operations for creating precise angular bends. These massive hydraulic press brakes can exert over 1,000 tons of force while maintaining positioning accuracy measured in millimeters. The tooling used here is specially designed for heavy gauge materials, with reinforced dies that can withstand the enormous forces involved. NTHE bending sequence is carefully programmed to prevent material distortion. Complex parts may require dozens of individual bends, each performed in a specific sequence to avoid interference with previously formed features. Computer-controlled bag gauges position the plate precisely for each bend, ensuring consistent angles and dimensions. And watch the operator using the touchscreen control system to adjust bending parameters in real time. The machine automatically calculates spring-back compensation, the tendency for thick steel to partially return to its original shape after bending. This ensures that the final angle matches the desired specification exactly. Quality control is integrated throughout the entire process. Here we see 3-dimensional measurement systems verifying that the finished components meet specification. These coordinate measuring machines can check dimensions, angles, and surface profiles with incredible accuracy. NTHE finishing operations include edge preparation, where automated systems remove sharp edges and prepare surfaces for welding or coating. Plasma cutting systems trim plates to final dimensions with computer-controlled precision. The heat-affected zones from cutting operations are carefully controlled to maintain material properties. NSUR face preparation is often the final step, with automated shot blasting or grinding systems creating the specified surface texture for subsequent coating or welding operations. Bremen Machinery's capabilities represent the pinnacle of heavy plate processing technology, where traditional metalworking craftsmanship meets cutting-edge automation and computer control. These massive steel components will serve in critical applications for decades to come, testament to the precision and quality achievable with modern manufacturing methods. Welcome to Dierstall, where we're witnessing the complete manufacturing process of a massive crankshaft, the critical component that converts the reciprocating motion of pistons into rotational power in large engines. These crankshafts will power everything from marine vessels to industrial generators, requiring absolute precision and incredible strength. NTHE process begins with a massive forging operation. Here we see a red-hot steel billet being shaped under enormous hydraulic pressure. This open die forging process gradually forms the basic crankshaft shape while maintaining the grain structure of the steel for maximum strength. NTHE forging press applies thousands of tons of pressure, literally reshaping the molecular structure of the steel to align the grain flow with the stress patterns the finished crankshaft will experience in service. This process creates a component that's far stronger than anything that could be machined from solid stock. Following forging, the crankshaft undergoes controlled heat treatment to achieve the desired mechanical properties. We're seeing the annealing process here, where the component is heated to precise temperatures and then cooled at controlled rates to relieve internal stresses and optimize hardness and toughness. And after heat treatment, the rough forging is prepared for machining. This includes shot blasting to remove scale and surface defects, followed by initial turning operations to establish reference surfaces for subsequent precision machining. Watch the precision turning of the main bearing journals. These must be perfectly round and smooth to ensure proper engine lubrication and minimal friction. The surface finish requirements are incredibly demanding, often measured in micro-inches of roughness. NNTHE final machining operations include grinding of critical surfaces to achieve the required dimensional accuracy and surface finish. These specialized grinding machines can maintain tolerances measured in 10,000ths of an inch across the entire length of the crankshaft. N-dynamic balancing is the final step, where the completed crankshaft is spun at high speed while sensors detect any imbalance. Material is precisely removed from specific locations to ensure smooth operation at all engine speeds. This crankshaft will now provide reliable service for decades in its intended application. Here at King Rock Drilling Tools Company, we're witnessing the precision manufacturing of hammer drilling tools, specialized equipment designed to penetrate the hardest rock formations in mining and construction applications. These tools must withstand tremendous impact forces while maintaining sharp cutting edges. An NTHE process begins with high-grade tool steel that's been specially formulated for impact applications. Watch as the raw steel bars are cut to length using precision sawing operations. The cut surfaces are then machined to ensure perfect perpendicularity and surface finish. End material traceability is critical here. Each piece of steel is tracked throughout the manufacturing process to ensure complete documentation of material properties and heat treatment history. This quality system ensures consistent performance in demanding drilling applications. NNTHE machining process begins with rough turning operations to establish the basic tool geometry. These specialized lathes are equipped with carbide tooling designed for the hard materials used in drilling tools. Notice the flood coolant system that prevents overheating and maintains tool life. Following rough machining, the drilling tools undergo precision grinding operations to achieve the exact dimensions and surface finish required. The grinding process creates the complex angles and relief surfaces that allow the tool to cut efficiently while clearing debris from the hole being drilled. Then heat treatment is absolutely critical for drilling tool performance. Here we see the controlled heating process, where the tools are brought to precise temperatures to achieve the optimal combination of hardness and toughness. The atmosphere in the furnace is carefully controlled to prevent oxidation and decarburization. NTHE quenching process rapidly cools the tools to lock in the desired metallurgical structure, followed by tempering to reduce brittleness while maintaining hardness. Temperature monitoring throughout this process ensures consistent results across all production batches. NNTHE final operations include precision grinding of cutting surfaces and quality inspection. Each tool is individually tested for hardness, dimensional accuracy, and surface finish. The cutting edges are inspected under magnification to ensure they meet the demanding specifications required for rock drilling applications. Welcome to Mannan Shahid Forgings Limited, where we're exploring the complete manufacturing process of automotive connecting rods, the critical components that transfer power from pistons to the crankshaft in internal combustion engines. These components must withstand enormous forces while maintaining precise dimensions for smooth engine operation. NNTHE process begins with precision forging, where heated steel billets are shaped under tremendous pressure in specially designed dies. Watch as the hydraulic forging press applies thousands of tons of force, literally flowing the metal into the exact shape of the die cavity. This closed die forging process creates the basic connecting rod shape while optimizing the grain structure of the steel for maximum strength. The flash excess material that flows out of the die parting line is carefully controlled to ensure complete die filling while minimizing waste. Following forging, the flash must be removed in a separate trimming operation. Here we see the forged connecting rods being positioned in a trimming press that removes the excess material with precision. After trimming, the rough forgings undergo shot blasting to remove scale and surface defects. This process also stress relieves the surface layers, improving the fatigue resistance of the finished component. The shot blasting parameters are carefully controlled to achieve the desired surface condition without overpeening the material. and heat treatment follows, with the connecting rods being heated to precise temperatures and then cooled at controlled rates to achieve the desired mechanical properties. This process optimizes the balance between strength, toughness, and fatigue resistance required for engine applications. Precision machining begins with the establishment of reference surfaces on specialized machining centers. These machines are designed specifically for connecting rod production with fixtures that securely hold the complex forged shape while providing access for multiple machining operations. NTHE big end bore, where the connecting rod attaches to the crankshaft, requires exceptional precision. Watch as the boring operation creates a perfectly round hole with surface finish measured in micro-inches. The concentricity between this bore and the small end bore is critical for proper engine operation. NTHE cap separation process is fascinating to observe. Here, the big end of the connecting rod is actually cracked apart rather than cut. This fracture splitting process creates perfectly matched surfaces that ensure precise reassembly and optimal load distribution in the finished engine. NNTHE, small end bore, receives similar precision treatment, with reaming and honing operations creating the exact dimensions required for the piston pin bearing. Surface finish is critical here, as this interface operates under boundary lubrication conditions in the engine. Weight balancing is performed on every connecting rod. Each component is weighed, and material is removed from specific locations to achieve precise weight targets. In high-performance engines, connecting rods in the same engine are matched to within grams of each other to ensure smooth operation. NTHE bolt holes for the big end cap receive final machining and thread preparation. These fasteners must withstand the enormous tensile loads generated by engine operation, so thread quality and dimensional accuracy are paramount. And every connecting rod undergoes comprehensive quality inspection, including dimensional verification, surface finish measurement, and material property testing. Magnetic particle inspection reveals any internal defects that could lead to failure under the cyclical loads of engine operation. These finished connecting rods now represent the perfect marriage of metallurgical engineering and precision manufacturing, ready to provide reliable service through hundreds of thousands of engine cycles. Welcome to Starco's Advanced Manufacturing Facility, where we're witnessing the complete production process of steel-spun wheels. These wheels combine the strength of steel with the precision of modern manufacturing to create products that serve in demanding agricultural and industrial applications worldwide. NNTHE process begins with high-quality steel sheet that meets strict specifications for strength and formability. Watch as precision plasma cutting systems create the initial wheel blanks from large steel sheets. These computer-controlled cutting systems achieve remarkably clean edges while minimizing heat-affected zones that could compromise material properties. NTHE cut blanks are then formed into cup shapes using powerful hydraulic presses. This deep drawing operation requires careful control of material flow to prevent wrinkles or tearing while achieving the desired shape. The forming dies are precision machined to create consistent results across thousands of production cycles. NNTHE's spinning operation requires skilled operators who can judge material flow and adjust tool pressure in real time. Modern CNC spinning lathes automate much of this process, but human expertise remains critical for achieving optimal results. The gradual forming action work hardens the steel, actually increasing its strength compared to the original material. And after welding, the wheels undergo stress-relieving heat treatment to remove welding stresses and optimize the metallurgical structure. This controlled heating and cooling process ensures dimensional stability and maximum fatigue life in service. NNTHE final operations include precision machining of mounting surfaces and bolt holes. These critical dimensions must be held to tight tolerances to ensure proper wheel balance and secure mounting. Computer-controlled machining centers achieve the required accuracy while maintaining high production rates. Each finished wheel undergoes comprehensive testing, including dimensional verification, balance checking, and pressure testing to simulate service conditions. Dynamic balance testing ensures smooth operation at all operating speeds, while pressure testing validates the structural integrity of the finished product.